In this video, we're going to talk about calculations of a pH of a strong acid or a strong base. So in this example, I'm going to calculate the pH of a 0.02 molar hydrochloric acid solution. Let's first review our different strong acids. We have 7 strong acids. So we have HCl, the one in this example, HI, hydrogen iodide, or hydroiodic acid, hydrobromic acid, nitric acid, sulfuric acid, perchloric acid, and then chloric acid. Those are our 7 strong acids. So whenever you approach one of those 7 acids in a problem, we're going to do it this way. So we want to first look at our reaction involved here. So we have hydrochloric acid completely dissociates into H plus and chloride ions, and we want to label it here as aqueous because we're in water. But that's not the only reaction present. Because we're in water, you always have to remember the autoionization of water reaction. So our water dissociates into hydrogen ions and hydroxide ions. So let's look at our major species. So because in my hydrochloric acid everything dissociates, I don't have much of the molecular form of HCl, but I have my H plus, my chlorine anions, and then because the water, we have a Kw of 1 times 10 to the minus 14. That means mostly I'm going to be favoring the reactants here, and so my major species is going to be water. So our third major species is going to be water. So, because of this, our H plus concentration is going to be dictated by the dissociation of HCl, and so our H plus is going to be 0.02 molar. So if we go to calculate the pH, we plug it into our negative log of H plus, and we're going to get 1.7 as our pH of HCl. So our next calculation, let's do another strong acid example. This time I'm going to have 1.8 times 10 to the minus 9 molar HCl solution. So we might be tempted to go ahead and just directly calculate the pH. And we get the pH equals negative log 1.8 times 10 to the minus 9. And you get a pH of 8.7. Now, we know that pH is greater than 7 give you a basic solution. So this is a pH of 8.7, therefore this is a base. Is that what's going on here? So we have to look more in depth into this calculation. Something is strange. So let's again look at our reactions involved. So we have our dissociation of HCl, and we have H plus and Cl minus, and we have our dissociation of water. And our Kw 1.0 10 to the minus 14. So just dissociation of water alone, let me step back just a second. So our dissociation of HCl is going to give us 1.8 10 to the minus 9th molar H plus. And our dissociation of water is going to give us about 1 times 10 to the minus 7th molar of H plus and OH minus. So actually in this case, our dissociation of water is our dominant reaction, producing the most H plus. So the pH in this case, if I take the negative log of 1 times 10 to the minus 7th, I'm going to get a pH of approximately 7, or neutral. The pH might be just slightly under, and you could go through a very long series of calculations to show that, because I have slightly more H plus than 1 times 10 to the minus 7. But this is 2 orders of magnitude less than the water, so the pH should be pretty close to 7. So that's something to watch out for. If you ever find that the concentration is significantly less than 1 times 10 to the minus 7, you're probably pretty close to a neutral solution. So let's look at one more calculation. pH of a strong base. Here we're going to look at the strong base potassium hydroxide. Sorry. 2.5 times 10 to the minus 3 molar potassium. So here, let's again look at our strong bases. Sodium hydroxide, potassium hydroxide, lithium hydroxide, calcium hydroxide, magnesium hydroxide. Those are our group 2 bases. I will point out that the group 2 bases, while they are strong bases, they're not very soluble in water. So we tend not to use them too much as in their role of a strong base. And there are some other group 1 strong bases, rubidium hydroxide, cesium hydroxide. However, again, those aren't very common. So these are the main ones you're going to be looking out for when dealing with the pH of a strong base. So again, now we've been warned based on the last example. We do still need to look at our reactions involved here. Potassium hydroxide dissociates as a strong base completely into potassium positive ions and hydroxide negative ions. And then we have our dissociation of water reaction as well. Our major species are going to be my potassium ions, my hydroxide ions, and also again my water. Based on the last example, we know we have to look at our concentrations to make sure we're dealing with the right thing. But here, if your concentration is significantly greater than 10 times 10 to the minus 1 times 10 to the minus 7, then the major reaction that we're going to deal with is going to be the base dissociation. So because 2.5 times 10 to the minus 3 is much greater than 1 times 10 to the minus 7, that first reaction is the most important. So we can go calculate our pOH. We'll use the pOH method. Negative log 2.5 times 10 to the minus 3. That gives me 2.6. And remember, we're not quite done. We have to use our relationship that pH is equal to 14 minus our pOH. And that is going to give us our final pH of 11.4. So now, with those, you can calculate pH of a strong acid or any strong base. And that is going to finish the topics through chapter 14.4. The next set of calculations we'll look at is going to be pH of a weak acid and weak base.